So this was a teaser regarding the motion into the 2D, right? The teaser regarding the motion into the 2D. First of all, if you all like this, right, I'll be waiting for all of your comments beneath the video regarding this teaser, I'm sorry, right? Yes, this is one of the treasure only. Okay, I will be waiting for all of your comments. Okay, so hello bacho, Sat Sri Akal and namaste from my side. Sat Sri Akal and namaste from my side, bacha ji, everyone. So this is your own physics educator Indrajit Singh, welcoming you all into the most sensible platform in the victory batch, into the pure English mode for the aspirants, right? Those who are preparing for JEE NEET kind of examination. Those who are preparing for JEE NEET kind of examination. How are you all? Yes or no? How are you all? So guys, we are back with, we started with units and measurement followed by motion in a 1D. Now today we are going to move forward into the 2D. Before moving forward, right, I need to discuss some of the important stuff here with you all, and it needs to be discussed. Why? Because you should have that kind of the psychology before moving on to this chapter. Generally, we are judging physics as horrible by its cover of the book, but physics is not as much as horrible as what you are thinking. If you can just turn out the physics books and read out the overview, whatever it is written, then things are going to be quite easy for you all. 99% of the students judges physics by its cover. Oh, physics. And before even reading a single statement, or before moving on for solving any single sum, they used to judge it out and have a, what we can say, the stamp on it that we are not going to. Physics is not our capability. We can't. It's not like that. Okay, there is always a requirement of physics. Okay, suppose let us take an example, right? If I'm talking about a pandemic, then there is a requirement to overcome the variant of a corona. That yes, compulsory we need an oxygen cylinder. Okay, else we can't treat you all. Okay, for fever we are having a specific requirement. Yeah, you have to, right, do rest for 1 or 2 days, and some precautionary measures you have to follow, and yes, things are going to be quite easy. For everything there is a procedure and there is a requirement that needs to follow to fulfill that task. Similarly, physics is also having that part, right? Physics is also having that part. Physics need your time. Physics needs your understanding, and most needed, right, is patience. If you are having these 3 things, you are going to crack, right? You are really going to crack. Yes or no? Right? Yes or no? Okay. So let's start with the motion into the 2D. The most of the required stuff into the motion in 2D is, vector. Okay. If you are dealing with vectors, if you are dealing well with vectors, motion in 2D and rest of the things are going to be quite easy for you all. Why a vector is needed? Sorry. In the entire universe, right, a scientist analyze, everything is not going in 1D. Because we are living into the 3-dimensional space, and the entire universe is distributed into the 11 dimensions as per string theory. Right? So it states that to represent the motion in 2D, we need a common thing. To represent the motion or all of the activities of all of those entities, those who are present in universe, we need a general or the common thing to represent all of those stuff into the 11 dimensions. For that reason, the vectors were introduced. Right? If motion of the particle is in 2D, yes, vectors can help. If motion of the particle is in 3D, yes, vectors can help. For that reasons, the vectors, in vectors we are having the three types of the quantities. The first one, that is a scalar quantity, vector quantity, and the tensor quantity. So vector, it is an important part in a motion into the 2D. Okay, so let's begin this stuff. In this lecture, we are going to move on for the projectile motion. All of those cases of the projectile motion, like horizontal projectile motion into an inclined plane, right? Okay, circular motion we will try to see, right, whether we are going to cover it or not. Okay, because the rainman problem and the riverman problem, these are the right awesome things, right, that needs more amount of the time, and unnecessary the lecture would be quite long. So I think this will, we will try to cover it with the, if possible, okay, then we will try right to cover this up with the work energy and power. The relative motion 1D and 2D, the rainman and the riverman problem, right? Okay, 1D relative motion we have discussed. Today we are going to discuss with the 2D, and the rainman and the riverman problems are one of the, what we can say, the applications of the relative motion only. So most probably in this lecture we are going to cover up the projectile motion, the cases of the projectile motion, riverman problem, rainman problem, right? Okay, and that's it. We will try, right, to cover it up the circular motion. Yes or no? Okay, so now let's move on to it. Let's start with the projectile motion. Now, lots of awesome things are going to come, right? Flow chart, it's okay. Projectile. What actually is a projectile is, according to the NCERT page number 77, this I used to mention in all of my lectures, in my previous series also, into the champion series, this thing has been already appeared, right? Okay. Projectile. What actually is a projectile? Right now I'm not moving on to that much technical definition, right? But just a simple meaning of the projectile motion is the thing that is thrown or released and is in a flight. An object or a particle in a flight, that's it, is a projectile motion. Whether it is thrown, whether it is released, and right, it is accelerated under the gravity, whether it is thrown at some specific angle. Let's take an example to understand this stuff, right? Suppose I am having this object into the hand, right? If it is released from this position, then it will accelerate under the constant acceleration towards the center of the earth. That is motion under gravity. Okay, suppose if it is thrown like this way, it will follow the, right, what path it will follow? 2D. A teacher throwing chalk on student, what path it follows? Like this way, the kind of the curve path or the parabolic path. Okay, so in all of those cases, one thing is common, that particle remained in the flight for small amount of the time, or n amount of the time, or for some specific amount of the time, the particle remained into the flight. So that states, that is the general definition of the projectile motion. Now, how we are going to classify the oblique projectile, the horizontal projectile, the projectile through the inclined plane, from all of those, right? From this general definition, it would be quite important, right? Now, what are the examples? An object in a flight after being thrown or projected, then it is known as the projectile motion. Now, what are the examples of it? The first one, right? Okay, cannon fire. You can see in this, it is inclined some I'm sorry, it is inclined at some angle and it is been fired, right? The ball follows a curvical path and it remains into the flight, right? It remains into the air for some amount of the time and it is a flight. So that's why this is an example of the projectile motion, right? Football kicks the ball. Footballer kicks the ball. Batsman hits the ball. Bowler bowls the ball. This all are the sort of example of the projectile motion. This all are the sort of example of the projectile motion. Right. Now, let's move on to the next thing. Right. This was a basic definition. Now, how the classification based on it is defined. Okay. Okay. There are basically three kind of the projectile motion that we are going to discuss. The first one, that is the oblique projectile motion. The second one, that is the horizontal projectile motion. And the third one, that is projectile motion from the inclined plane. Oblique projectile motion, horizontal projectile motion from the inclined plane. Oblique projectile motion, horizontal projectile motion from the inclined plane. Yes or no? Okay. So, what actually it is? What is the difference between these two? These all are the projectiles, because in all of those examples, the particles are remaining into the flight. See, entire projectile, if I'm talking about it, is only based on the single concept, right? It is based on the single logic. Okay, it is based on the single logic that you need to be aware of. Okay, and small modifications into it. Okay, things are gonna be quite easy. Okay, small modifications into it, things are gonna be quite easy. Okay, so this was the classification of the projectile motion. Now let's move forward, okay, to the actual logic. Okay, there are some assumptions into the projectile. Generally, practically, see, there is a lot of difference between the theoretical physics and the practical physics. Lots of difference. Okay, lots of difference between the theoretical physics and the practical physics. Whatever the theoretical it is going on for the understanding purpose, we used to have some assumptions into it to understand it theoretically. Right? Like, suppose if I'm throwing the object is released in the practical life, suppose if I'm taking an example, the object is released from some height. Is it possible that air resistance is not acting on it? Nope. But whatever the output I'm expecting, that is getting disturbed, right, as because of this air resistance. So for the theoretical purpose, for the theoretical this calculations, we are having the first assumption that air resistance is absent. First of all, from the earth atmosphere, right, absence of air, right, won't take place, and it is not going to be possible. If it is going to be possible, then how we are going to define all of those stuff and how we are going to breathe. But practically, whatever the calculations, whatever the numericals we are going to solve, this air resistance factor is really going to affect it. So for that reason, I have taken the first assumption, theoretical assumption, right? Sometimes the logic helps us in understanding the topic. Sometimes the difference between the practical life and whatever the understanding we are having into the theoretical matters, right? This difference helps us in understanding the logic behind the specific topic. Okay, so there are some assumptions we are taking into the projectile motion. The first one, that is air resistance is completely absent. The effect due to the curvature of the earth, we are taking it as negligible. As I have told you all, into the motion into the 1D, there were we have taken some assumptions in which, right, value of the G is getting affected. This thing we are going to see into the gravitation chapter, right? There are some factors, there are some things, right, through which value of G may get affected. All of those things, right, are going to come up into the assumption. The value of the G that affects is because of the altitude, latitude, right, and as because of the rotation, lots of things are there. So all of those things we have taken into the assumption. All of those things we have taken into the assumptions, right? So air resistance is always absent. The effect due to the curvature of the earth is negligible. The third one, rotation of the earth, as because of the rotation of the earth, right, as because of the curvature, things are getting affected, our output will get disturbed, right? So for that reason, the effect of the rotation of the earth is always avoided. Okay, And there are chances. See, whatever the assumptions we are going on, whatever the things we are going there, we are dealing with theoretically. So there is a possible theoretically I'm giving the theoretically I'm giving the speed to an object whose value will be more than the escape speed, because whatever the speed I'm giving, it is theoretically, not practically. Practically to give the speed of light is not possible. Suppose I'm throwing an object with the speed of light, obviously it is going to immediately evacuate right from the gravitational space of the earth, gravitational field of the earth, because things are going on theoretically na, so anything may happen. For that, one theoretical assumption is going to come upon: always throw the object into the projectile less than the escape speed of the earth. Always throw the projectile right less than the escape speed of the earth. Yes or no? Oblique projectile. As into the champion series also, lots of Indrajit search were coming on. Right, here also we are going to take the same example, but things are going to be quite different. Projectile needs to be understood into the different manner. Things are going to be quite easy, I guarantee. Oblique projectile. When a particle is thrown with some velocity u, right, at some angle theta with respect to ground or with respect to horizontal, then the particle follows the specific trajectory. This trajectory, it is known as the projectile motion. This trajectory, it is known as the projectile motion. This trajectory, it is known as the projectile motion. Okay, it is thrown at some velocity, it is thrown at some specific angle. Right. Now, oblique projectile is having some specific logic to understand, right? And with that some specific logic, there is a special way to solve all of those sums of the oblique projectile motion into the convenient manner. Sometimes it is important to follow the right approach. Yes, I want to reach the United States, right? But we need to follow the appropriate approach. From either Bombay to Delhi, I'm going to take up the flight. Okay, either I'm going to take up the 16 hours of the direct flight to reach the USA, or the second option would be I'm going to move on from either Amsterdam, right, or a specific thing like Dubai. Okay, and I'm going to break up my journey into the two parts. But it is inappropriate, okay, first of all to move on for this Singapore, then to move on for the Spain and Turkey, then we are moving forward to the Amsterdam, then we are moving forward to the United Kingdom, UK, and then we are moving forward to the Canada, and then we are moving forward to the, right. So sometimes if the students are following the second approach, then it feels like, oh, physics is hack. But here we are not talking about that stuff. You need to follow the appropriate approach. The consequences of following the wrong approach will be having the disastrous effect of physics in your life. They will have an disastrous impact in name of the physics in your life, and you need to obviously on the study preparation. Okay, so for the projectile, right, what we need to be approach. See, projectile is nothing. If I am talking about this velocity, then it can be broken into the two components. The u cos theta is an horizontal component. This one is a u sin theta, and it is the vertical component. U cos theta is an horizontal component. U sin theta is a vertical component. Right? U cos theta is a horizontal component. Right? U sin theta is the vertical component. As the motion is 2D, as the motion is 2D, it means that two individual 1D phenomena give resultant as 2D. Two individual 1D phenomena give resultant as 2D. It means that in the projectile, if this motion is in 2D, something is going on into the horizontal part, something is going on into the vertical part. The resultant of both individual 1D processes that are going on simultaneously, resultant of that is a 2D and a projectile. Okay, resultant of that is the 2D or the projectile. Yes or no? Yes or no, students? Right. So here what I'm talking about, when an object is projected at some specific angle with respect to the horizontal, right, then we can say, so here something is going on into the horizontal part, something is going on into the vertical part. As a resultant of, right, this two individual 1D phenomena that are going on simultaneously, two individual 1D phenomena that are going on simultaneously, mark my words, two individual 1D phenomena that are going on simultaneously, then this kind of the motion, it is known as the resultant of this is a 2D, and that is an oblique projectile. So in another sense, can I say, if I want to represent this stuff, can I say the projectile is something that is contributing into the horizontal direction, right? Something that is contributing into the horizontal direction, right? Plus something that is contributing into the vertical direction. Okay. Projectile is something into the horizontal plus vertical. We have to understand the nature of the horizontal motion and apply the relevant equation. We have to understand the nature of the vertical motion and apply the relevant equations. Then things are going to be quite easy for you all. Right? What will be the nature of horizontal? What will be the nature of the vertical? Represent into the vector form. Projectile will be quite easy for you all. Right? Projectile is going to be quite easy for you all. Right? Yes or no, everyone? Okay. So, let's analyze the nature of the horizontal and the vertical part. Now see, first of the assumption we took that air resistance is absent. Right, the one of the assumptions into the projectile motion is air resistance is absent. Now in the absence of the air resistance, see, air resistance is absent, right? It means what is going to happen? We are having no horizontal acceleration. We are having no horizontal component of the acceleration to increase or decrease the u cos theta component of the velocity. Right? No horizontal acceleration is there because air resistance is absent. Okay? No horizontal resistance is there because air resistance is absent. It means that, see, whenever the acceleration is in direction of the velocity, it is going to speed up this object. Whenever the acceleration is in opposite direction of the velocity, it is going to speed down the object. Okay. So in this case, what actual it is going on? Okay. In this case, what actual it is going on? Okay. What actually things are going on that I'm going to discuss in front of you all. Okay. Here, velocity component is there, but to increase or decrease this velocity component, we are not having any kind of the acceleration in the direction or the opposite direction of velocity. So it means that if I'm talking about the horizontal motion, then this horizontal motion, right, in which the u cos theta component is going to be constant, right? And this velocity being the constant, then I must say this horizontal motion of the projectile is the uniform motion, right? Horizontal motion of the projectile, it is known as what? Uniform. Why it is a nature of the horizontal motion that is uniform? Why? u cos theta is constant. Why u cos theta is constant? Because we are having no air resistance, right, horizontally acting, or that has capability to increase or decrease this value of u cos theta. So one thing we are defined, what? The air resistance is completely avoided in the horizontal nature. The nature of the horizontal motion of the projectile is uniform. What about the vertical part? The vertical component of the velocity is u sin theta. U sin theta is acting into the upward direction, G is acting into the downward direction. It means that to increase or decrease the value of u sin theta, we are having the constant acceleration. What it is going to happen at the topmost point, the u sin theta value is going to be 0, right? And at the point where it hits, u sin theta is going to be negative maximum. Here it is maximum. Here u sin theta, the vertical component of the velocity, is 0, right? And here it is again maximum into the negative side. Variations are there, na? In horizontal component, we were having only u cos theta. Here also the value is u cos theta. Here also is u cos theta on each and every point, right, on the path of the projectile. The horizontal component is u cos theta. So that's why we declared the horizontal motion as a uniform motion. But here the value of the vertical component of the velocity is getting changed from the point of projection to the point where it strikes. From the point of projection to the point where it strikes. So in this case, what is going to happen? It means that vertical velocity is anyhow getting affected. Who is going to affect that part? Gravitational acceleration. Who is going to affect that part? Gravitational acceleration. It means that vertical motion will be uniformly accelerated motion. Vertical motion will be uniformly accelerated motion. So it means that if I am talking about the projectile, then it is a resultant of the horizontal part, that is uniform motion, plus vertical part, that is uniformly accelerated motion. This is the actual logic of the projectile motion, and we are going to combine the horizontal and vertical both at once at the same time, because it is going to help us, right, in saving our time and understanding the concept well, right? Yes or no? Yes or no? Okay. So it is a combination of the uniform motion and the uniformly accelerated motion. It means that if we're talking about the horizontal part, all of those equations of the uniform motion are applicable to the horizontal motion. All of the equations of the uniformly accelerated motions are applicable to the, right, the the vertical part. This is the way or approach we are going to see the projectile motion. This is the way or the approach we are going to see into the projectile motion. Yes or no? Okay. So now, analysis. The detailed analysis states that this is the path of the projectile. This one is the vertical component of the velocity. This one is the horizontal component of the velocity, right? Horizontal component is affected by no acceleration. Vertical component is accelerated by the, right, gravitational acceleration. This is what the detailed analysis is all about. Okay, this is the detailed analysis all about for the oblique projectile motion. Right, the detailed analysis of the oblique projectile motion. Okay, let's move on to the next question onto it. What will be the question solving approach? Okay, directly we are going to discuss, right? We have seen. Okay, now we are going to discuss the parameters, those who are involved into the, right, the projectile motion, the parameters that are, right, involved into the motion parameters, right? The first thing is time of flight. Okay, the same logic we are going to use, just hold on, right? The same logic we are going to use. I'm sorry, just hold on for a second. Okay. Now, what happens here? Time of flight. This is a trajectory of the projectile the particle is going to follow. The trajectory of the projectile the particle is going to be follow. Right? Okay. Obviously, contribution of the horizontal component, contribution of the vertical component. Now, what happens here? Horizontal component is constant. At t is equal to 0, the particle is projected from the POP. POP stands for point of projection. When it strikes the ground, the vertical height is getting 0. Right? What is logic behind it? When it strikes the ground, vertical height is getting 0. Vertical height is getting 0. I'm sorry for this. Okay. Now, how to identify the equation of the vertical height? So, before moving on to the time of flight, first of all, let's move on to the position and the velocity vector. Right? If this will be understood by you all of the equations of the projectile motion will be into the fingertips on your hands. Right? At t is equal to 0, right, particle is projected with some velocity u. At t is equal to 0, particle is projected with some velocity u. Horizontal component is u cos theta, vertical component is u sin of theta. With respect to point of projection and t is equal to 0, what is the position of the particle after t1 seconds? What is the position of the particle after t2 seconds? What is the position of the particle after t3? What is the position of the particle after t4? What is the position of the particle after t5? What is the position of the particle after t6? What is the position after the particle t7? What is the position at t8? What is the position at time of flight? Position with respect to the point of projection is getting continuously changed. And position is the vector quantity. So for that reason, see, initially position is this, then position is this, then the vector is this, vector is this, like this way, like this way, like this way, like this way, finally merging up with the horizontal. So this is the reason when it strikes, the height is getting 0. But how we are going to define this position vector? This is a vector, na, it is getting changed. Right? The position vector is getting changed. Then how we are going to define that stuff? Okay, how we are going to define that stuff? As usual, projectile, it is the combination of the horizontal part plus vertical part. Projectile is the combination of horizontal part plus vertical part. Horizontal, see, this is the position vector. Right? If I am defining into the vector form, then there might be some x component, there might be some y component. How I am going to define the x component? On basis of the nature of the motion. X is uniform, velocity is constant. It means at every time t, this x distance is increasing with respect to time. Can I say this displacement is velocity into time? Because it is a uniform motion. What about vertical? Initially height was this, then height was this, then height was this, then height was this. Now height is decreasing. So what is the nature of the vertical motion? Uniformly accelerated. So it states that Ry is going to affect, like initial velocity is u sine theta of t minus half gt square. All the right equations of uniform motion are applicable to the horizontal part. All of the equations of uniformly accelerated motions are applicable to the vertical part. Combination of this that is going on simultaneously is a projectile. This is how the position vector is defined, right? Continuously, position vector is changing the angle. See, continuously, right, the position vector is changing the angle. Initially phi was this, now angle is this, now angle is this, now angle is this. See, angle is decreasing. Finally, it becomes 0 with respect to horizontal. So how we are going to define? See, this is my position vector r. This is my position vector r at any time t. So how that angle, it is making angle with respect to horizontal, that is ry by rx. Ry by rx. How? If I'm talking about this position, this is r of y, this is r of x, this is angle. Right? I can say there, right? This is r of y, this is r of x, this is angle, right? And this is my position vector r. With respect to time, ry is changing. With respect to time, rx is changing. With respect to time, angle is changing. So we can say the angle as tan inverse of, right, what is the y component? U sine of theta minus half of gt whole divided by u cos of theta. 1t will get cancelled. This is the position vector of a particle at any time t. This is the angle that it makes with respect to the horizontal. Angle it makes with respect to the horizontal. The same concept we are going to use, right, for the velocity. Two components. Projectile is thrown at t is equal to 0 at some specific time t. Right, this is a vertical component u sine of theta. This is the horizontal component u cos of theta. Vertical component u sine of theta, horizontal component u cos of theta. Right. Initially vector is this. At the maximum height, vector is going to be u cos theta only. When it strikes, vector is going to be u sine theta, right, u cos of theta, and this will be the, right, final v. Okay, this will be final v. right? So the initial velocity vector is this, final velocity vector is this, right? The direction of the vector and the values both are getting changed in between the initial and the final position, na? So how we are going to define the velocity at any time t? Simple. The velocity vector, how we are going to define the velocity at any time t, right? The velocity vector, again, it is something that is contributed into the x direction, something that is contributed into the y direction. X is constant. It is a case of uniform motion. So the velocity component is going to be constant u cos theta of I. Vertical component is first getting decreasing to 0 and it is again getting increased into the negative direction. It means, as I said before, that something is present which is decelerating and accelerating this u sin theta. So vertical is uniformly accelerated, so I can say it is u sin theta minus gt. I am applying the equation of uniformly accelerated motion, the velocity equation of the uniformly accelerated motion. So this is the equation of the velocity at any time t, right? Equation of the velocity at any time t. At the different position I am talking about. At the different position I am talking about. This is position 1, this is position 2, this is position 3, this is position 4, this is position 5, 6 and final when it hits. Here velocity vector is like this way. Here velocity vector is this way. Here velocity vector is this. Here velocity vector is this. Here velocity vector is this. See, it is changing now. If it is changing, right, its horizontal is constant but vertical is changing with respect to time. So at every moment, right, at every moment it is changing the angle. See, this is Vy, this is Vx, this is gonna be angle phi. At this point, this will be Vx, this will be Vy, this is gonna be phi. And here phi is 0. Here this is gonna be Vx and this is gonna be V of y. Here this is gonna be Vx, here this is Vy. Right? At every point the angle is also changing with respect to time. So this angle we are going to define it as the vertical component of velocity by horizontal component. Okay, so this is going to be u of sine of theta minus g of t whole divided by u cos of theta. So this is the equation of the velocity vector and the angle. Okay, there is a difference. Position vector makes angle with respect to point of projection. Velocity vector makes an angle with respect to horizontal. This is a difference. Angle with respect to the horizontal. Right? Yes or no? Angle with respect to the horizontal. Yes or no? Right? Now on basis of this we are going to define the time of flight. When it strikes the ground, Ry component is getting 0. What was the value of the Ry component? U sine of theta of t minus half gt square. This is getting 0. It means that u sine of theta into t, that is equal to half of gt square. Time of flight is equal to 2u sine of theta by g. Time of flight is 2u sine of theta by g. Similarly, time to reach max height, u sine of theta by g. Right? Time of flight 2u sin theta by g. Time to reach max height, half of the time of the flight, right? This is equal to time of flight, right, by 2. See now how things are gonna be quite easy, and immediately, right, we are going to analyze the equation. Equation of trajectory. See, trajectory is always a relation between y and x. Rx is equal to u cos of theta into t, right? Ry is equal to u sine of theta into t minus half of gt square. This is x, this is y. Relation between x and y, one expression is coming out. That expression is the trajectory of the projectile, the parabolic kind of trajectory, right? This is a parabolic kind of trajectory, na? Right? So can I say that, right, t is equal to x by u cos of theta? Can I replace it here? Y is equal to u sine of theta of t minus half gt square. Replacing the value of t, y is equal to u sine of theta into x whole divided by u cos of theta minus g by 2, right, x square whole divided by u square cos square theta, right? So the equation of the trajectory that is coming out as y is equal to x sine theta minus gx square by 2 u square cos square theta. This is the equation of the trajectory of the projectile. See how easily. First of all, approach is important. If we are approaching the position when the velocity vector at time t, things are going to be quite easy, right? Approaching the velocity vector and the position vector at time t. Another equation of the trajectory is there, x sin of theta, right, 1 minus x by r, right? R is a range. Okay, maximum questions are asked on the second equation. Range, maximum, or you can say the horizontal distance covered in projectile, not maximum, right? Horizontal distance covered into the projectile. Okay, so that Rx is equal to u cos of theta into t. If I am replacing t as time of flight, things are gonna be quite easy. So by replacing this t as time of flight, right, the range equation is coming like this way, u square sine 2 theta by g. Equation of the maximum height. Here we are having u sine theta. This will be the max height. Here u sine theta is 0. Can I see vertical motion is uniformly accelerated? Can I apply the third equation of motion between the t is equal to 0 to max height? H max is equal to u square sine square theta whole divided by 2g. This is the equation of max height. Rapidly we are doing this. Equation of the linear momentum. Linear momentum is a vector quantity that is mass into the velocity, right? Are we aware of the velocity vector? Yes or no? Yes. U cos theta of I plus u sine of theta minus gt, right, of j. This is your momentum vector. Momentum vector is always parallel to the velocity vector only, right? It is always parallel to the velocity vector only. So this is how momentum is defined. Angular momentum, right? Angular momentum into the vector form, right? It is r cross p, right? It means cross product of position vector and the momentum vector, we are going to get the angular momentum, and it is a vector quantity. So how we are going to define that stuff, right? Okay, see, r vector is u cos of theta of t of I plus u sine of theta of t minus half gt square of j. P vector, that is equal to m u cos theta of I plus u sine of theta minus gt of j. R cross P, you have seen into the basics of the vectors to find out the cross product, right? You have seen into the basics of the vectors to find out the cross product. It is important, right, to keep that into the determinant form. I j k. First of all, place the r. U cos theta of t, u sin theta of t minus half gt square 0. Right? Place momentum mu cos of theta, right? Mu sin of theta minus mgt 0. Right? This is the expression I have kept it up, right? Okay. Or let us take an example. You are having the position vector I plus 3j. You are having the momentum vector 4i plus 3j, right? So how you are going to define the angular momentum? I, j, k, right? 1, 3, 0, 4, 3, 0. Whatever the value it is coming, it is the variation of the angular momentum vector. This thing I have shown you all in front of, in the terms of example. This is a general expression. Please don't get scared. Right? A general logic of the vector it is used. That's why I told you all into the beginning. While dealing with the 2D, vector is important. While dealing with the 2D, vector is important. Right? Yes or no? Okay. Let's move on to the next question onto it. Energy. All of these things, they are up to NEET or JEE level, right? Energy, kinetic energy, potential energy. See. Okay. Velocity variations are there, na? Then how we are going to define the kinetic energy? That is half mv square, right? So kinetic energy is equal to half m. U square cos square theta plus u sin theta minus gt whole square. This is the equation of kinetic energy, because this is V is velocity at any time t. Right? What is the equation of potential energy? See, with respect to ground, the potential energy is also getting changed, na? Right? So potential energy, that is equal to mg r of y. Right? So it is m of g u sin theta of t minus half gt square. This is how the potential energy is changing with respect to time. What will be the total energy? Right? Total energy, that is equal to kinetic energy plus potential energy. At any point, right, using these two equations, you can define the potential total energy at, right? You can define the total energy. Okay, this is how the terminologies into the projectile is defined. Radius of curvature. Okay, this thing we are going to see in some. No worries. A projectile is fired from the surface of the earth with velocity of 5 meters per second at an angle theta with respect to horizontal. Another projectile is fired right from another planet with the velocity of 3 meters per second. at the same angle follows a trajectory which is identical to the projectile that is fired from the earth. The value of the acceleration due to the gravity on that planet will be what? Right. Now we are going to see some of the questions basis, right, on the projectile motion. Okay, we are going to see some of the sums based on the projectile motion. Okay. Projectile is fired. See, here we are comparing the two things. The first one is Earth and second one it is a planet. Projectile is fired. Projectile is fired. At one side it is fired at 5 meters per second. At another side it is fired with 3 meters per second. This is the theta. This is the theta. In both of them, they are following the same trajectory. Right? Both of them, right, are following the same trajectory. It means that it is very simple thing. Right? Both are having the same max height and same range. Max height may get differ, but both are having the same range. Right? Okay, right. Another projectile fired from the planet with 3 at the same angle, right? Angle is same, follows a trajectory which is identical with the trajectory of the projectile from. Trajectory is also identical. Yes, it means H max is also identical. Okay. U square is directly proportional to G. How we got this? Trajectory is identical. It means H max is same in both of these cases and range is also same. Only the value of the gravitational acceleration is getting different. Value of the gravitational acceleration is getting different. Right. So what happens here? Right. From this equation, u1 square by u2 square, that is equal to gravitational acceleration of Earth by gravitational acceleration of planet. From Earth it is fired at 25 by 9, that is GE by G of P, right? So gravitational acceleration of planet is 9 by 25, right, into gravitational acceleration of Earth is 10, right? Approximately 3.5. Nearly about, right, 3.5 it is going to come. More than 3.5 is going to come, but the nearest answer is 3.5. Right? This is a perfect answer for this specific question. The velocity of the projectile at the initial point is 2I plus 3J. Right? Velocity of the projectile at the initial point is 2I plus 3J. Right? Initial velocity, that is equal to 2I plus 3 of J. Its velocity at point B will be what? Point B, it means where it strikes. Right? Point B, it means where it strikes. So it's a very simple thing, right? The horizontal component of the velocity is going to be 2 meters per second. This is gonna be 3 meters per second. Now when it strikes, the vertical component is going to get reverse, -3. The horizontal component is going to be constant. So when it strikes, the velocity it is going to be -3 of I, -3 of J plus 2 of I. So it's 2I minus 3J. A is the perfect answer for this specific question. Right? A is the perfect answer for this specific question. Yes or no? Let's move on to the next question. Two projectiles of the same mass with the same velocity are thrown at angle 60 degree and 30 degree with the horizontal. Then which will remain same? See, this is one of the special case of the projectile motion. Suppose if one projectile is thrown as theta with you, second is also thrown at you, but it is thrown at a 90 minus theta. Whenever this kind of situation appears, right? Whenever this kind of the situation appears, both are thrown at the same velocity, but one is at theta, second is at 90 minus theta, right? Then the ranges of the both are same. This is a spatial. With the range, we are having another two formulas, right? First of all, what is the formula of range? That is u square into 2 sine of theta cos of theta by g. Let's say this is R1 when the particle is thrown at theta. What about R2? It is thrown at 90 minus theta to 2 sine of 90 minus theta cos of 90 minus theta whole divided by g. R1 is equivalent to R2. Range is same when this kind of the situation appears. Apart from this, right, some more questions are asked into an examination, right, and that states that the ratio of the time of flight, that is equal to tan of theta, and the ratio of the max height, that is equal to tan square theta. Right. These two are the additional information on which the questions are asked into the examination. The range of the projectile is same. The range of the projectile will remain same. Right? Let's move on to the next question. Projectile is fired at the 45 degree with respect to, right, the elevation angle of the projectile at its highest point seen from the, see, here comes the question of the elevation angle. T is equal to 0, projectile is fired at theta. At the max height position, what is the elevation angle? This will be the elevation angle. What will be the elevation angle? This will be the elevation angle H max. This is R by 2. Elevation angle, if this is 90 degree, then elevation angle it is going to come upon H max whole divided by R by 2. Right. Now it is thrown at 45 degree. See, mark my words, it is thrown at 45 degree. Right, H max is u square sine square 45 whole divided by 2g, right, into u square, right, okay, into sine of 2 theta, it means 90 whole divided by g, and again into 2, right, u square cancel, right, u square cancel, 2 cancel, g cancel, this sine theta is 1, right, tan of phi, it is going to be half, the elevation angle it is going to be tan inverse of half, right. C is the perfect answer for this specific question. Okay, very easy. This formula we have seen, Ry by Rx, right? Okay. The speed of the projectile is maximum at its maximum height is half of the initial speed. At maximum height, the speed is half of its initial speed. Speed at H max, that is equal to half of initial. Speed at the max height, u cos of theta. Initial speed, u is gonna get cancelled. Cos theta is half, right? Theta is equal to 60 degree. This is angle of projection. The angle with which the projectile is projected. 60 degree is the perfect answer for this specific question. Particle is dropped from the height and another particle is projected into the horizontal direction with speed 5 meter per second from the same height. Then the correct statement is what? Two things we are going to compare in this question. I'm moving aside for the 10 seconds. If you want to solve it, you can. Okay, under countdown of 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Particle A is dropped from the height. This is height h. Particle A is dropped, u is equal to 0. Second is thrown with the 5 meter per second. Now this is the case of the from the same height. One is going to follow the motion under gravity. Second is going to follow the horizontal projectile motion. Right? Both of them are having the same time of flight. In the case of the motion under gravity, time of flight is same, right? Okay, the formula is same. In the horizontal projectile, we are going to see this formula, don't get worried, right? Both of the cases, time of flight is same. It means both particles will reach the ground simultaneously because they are released from the same height irrespective of the velocity. Velocity doesn't matter. They are released from the same height. Right? Velocity doesn't matter. They are released from the same height. Maximum range of the projectile is 16 kilometer. Then the muzzle velocity of the shell will be what? 16 kilometer. Now here comes the maximum range. Whenever this word is used, the maximum range, it means, right, the projectile is projected at 45 degree. Projectile is projected at 45 degree. So Rmax, it is going to be u square whole divided by g. So u square, it is 16,000 meter, right, again into 10. So u square is equal to 16 into 10 to the power 4. U is equal to 4 into 10 to the power 2. 400 meter per second. This is the muzzle velocity. C is the perfect answer. Right. This is how the questions are going to come from the projectile. Now let's come to the next part. If projectile is easy, it is easily understood by you all, then the horizontal projectile and the projectile at the inclined plane will be on the tip of the hands. If the logic of the oblique projectile is understood by you all, right, then this thing is gonna be quite easy. Right? This thing is gonna be quite easy. How? Simple thing is that horizontal projectile in the oblique projectile, with respect to horizontal, particle was thrown with respect to at some specific angle. In horizontal projectile, right, particle is thrown with horizontal velocity u from height h. Particle thrown h. Then it follows a specific trajectory. This is the trajectory of the horizontal projectile. Same concept. Horizontal projectile motion, it is a combination of something that is contributed into the horizontal direction, something that is contributed into the vertical direction. Something that is contributed into the horizontal direction, something that is contributed into the vertical direction. Okay, but here again no air resistance is present, right? Initial vertical velocity is 0. There is a small difference between the oblique and horizontal projectile motion. Initial vertical velocity was there, but here the initial vertical velocity is 0. And that thing is going to make the horizontal projectile motion quite easy. Right? No horizontal acceleration. It means the nature of the horizontal motion is uniform. Right? G is going to affect its vertical velocity slowly. It is going to increase the vertical component. So the vertical, right, will be the uniformly accelerated. Vertical will be the uniformly accelerated. Time of flight. Thrown with you, it is following this kind of the trajectory. What will be the time of flight? Before moving on to the time of flight, let's move on to the position at any time t and the velocity at any time t. Okay, like we did into the oblique projectile motion. See, same. Thrown with the horizontal u, this is the trajectory, this is thrown from some height h. Position at any time. See, at t is equal to 0, this is a point of projection. Here it is thrown. This is position at time t1, time t2, time t3, t4, t5, time of flight. Here position is this. Now position is changing to this. Now changing to this. Now changing to this. Now changing to this. Now changing to this. This is how the position right into the horizontal projectile motion is getting changed. So that is something that is contributed into x, something that is contributed into y. X is, in previous case it was u cos theta into t, but here it is thrown with u, so it is u into t. In previous case, it was u sine of theta of t minus half gt square. But here the vertical component is 0. In the oblique projectile motion, u sine theta is 0 at point of projection. It means that this u sine theta we are going to remove. Right? And we are only going to write it as plus negative of half gt square of j. This is the position vector with respect to t. Now, what angle it is changing? First angle is this, angle is this, third angle is this, fourth angle is this, fifth angle is this, sixth angle is this. Angle is increasing with respect to time. Right. So that angle it is defined as tan of phi. It will be negative. Is negative of half gt square whole divided by ut. 1t will get cancelled. Tan of phi is equal to negative of gt by 2u. This is an angle that the position vector is changing. Right, the position vector is making with respect to horizontal. Velocity similarly. Velocity vector, it is u cos of theta of I plus u sine of theta, right, minus gt of j. This we were writing into the oblique projectile. Into the horizontal projectile, HPM stands for horizontal projectile motion. In horizontal projectile motion, we are writing it as v. U cos theta is u. U sine theta is 0 minus gt of j. This is the equation of velocity. Here it is u, slowly, right, the vector is getting changed like this way. On a curvical path, tangent to the path, its velocity. What angle it is making with respect to time? Minus gt by u. It's vy by vx. time of flight, r of y is going to be negative h. According to the sign conventions, it is in negative direction, na? Right? So that is equal to negative of half gt square. Time of flight, it is going to come upon as under root of 2h by g. Rapidly things are going on, right? Equation of trajectory. Relation between y and x. X is equal to ut. Y is equal to negative of half gt square. Right? Okay. So replacing x in y, you are getting y is equal to negative of half of g into x square by u square. Y is equal to negative gx square whole divided by 2u square. This is the equation of trajectory of the horizontal projectile motion. Range. Now this is going to be quite easy. Sorry. Range is horizontal component into time of flight. Time of flight. So this is going to be u under root of 2h by g. Like in this case also, on basis of the position vector and the velocity vector, right, momentum is defined, angular momentum is defined, kinetic energy, potential energy, total energy, everything is defined. Maximum height is going to be h only. Okay, this question is nice. I am going to give you all in a homework, right? This is a very nice question. I want you all to answer this question beneath the video, right? I want you all to answer this question beneath the video. Okay, yes or no? Okay, very nice question it is. Okay, now see, directly formula based questions are going to come. A bullet is dropped from the same height when another bullet is fired horizontally. See, one bullet is fired horizontally, second bullet is dropped. We got the answer, yes or no? The thing that is dropped, it is also having the time of flight formula under root of 2h by g. The thing that is been fired horizontally, it means it is a case of the horizontal projectile motion. It is also having the formula of 2h by g. Now both are released from the same height. It means time of flight is gonna be same. So when they are going to hit the ground, simultaneously they are going to hit the ground. Why simultaneously they are going to hit the ground? Because time of flight in both of the cases is same. I'm sorry. Time of flight in both of the cases is same. Aeroplane is flying at the constant horizontal velocity of 600 km per hour at an elevation of 6 km. At an appropriate time, pilot releases the ball so that it strikes the target. Right. The ball appear to be falling at. See, this is ground. At the elevation of 6 km, aeroplane is moving. The one who is observing on ground, let's take two observer. One who is observing on ground, see, whatever the bomb it is released, if the plane is having the horizontal velocity, it means whatever the bomb is present inside it, it is also having some horizontal velocity. So it means that bomb is released with the horizontal velocity and it is going to follow the horizontal projectile motion trajectory. Horizontal projectile motion trajectory. With respect to observer on the ground, but with respect to the pilot, it is dropped vertically down. Observer position is getting changed, things are getting changed. Observer position is getting changed, things are getting changed. Yes or no? Right. So it follows the parabolic path as seen by pilot on the plane, wrong. vertically along the straight path as seen by observer on the ground. Wrong. By observer on the ground, it is a horizontal projectile motion. By pilot, why when pilot sees, then it falls vertically down? Because see, horizontal component of the bomb is V. Same is the horizontal component of the pilot. So the horizontal relative will be 0. Only vertical effect will appear. On parabolic path as observed from the target, this is the perfect answer for the specific question. I'm moving aside on the countdown of 10 seconds. If you want to analyze, this is a very nice question. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. A bomb is dropped from an aeroplane moving horizontally at the constant speed. See, it is thrown with you. This is a case of horizontal projectile motion when air resistance is avoided. Suppose if air resistance is taken into the consideration, right, it means that bomb is going to affect by the horizontal acceleration and vertical acceleration both, right? This is the horizontal component of acceleration, that is resistance by air. This is vertical, and even G is also acting. Okay, so it means the horizontal component will try to drift, right, particle towards the left side if air resistance is avoided. It means if air resistance is neglected, it is going to hit at this point. If air resistance is taken into the consideration, right, then it is going to hit at this point. Right. So when it hits, plane is here. When it released, plane was here. When it hits, the plane is here. If air resistance is avoided, plane is exactly below the bomb. But when air resistance is taken into the consideration, plane is ahead, bomb is behind. This question is going to give to all homework in my side. Right? Homework from my side. Right? Okay. Now let's move on to the inclined plane projectile motion. This is gonna be quite easy. Okay. In which here we have to remember only two formulas. Okay. Rest of the formulas are quite complex. Okay. Rest of the formulas are really complex. So we are not going to deal with that stuff. We are going to define this part only. Inclined plane projectile motion. Particle is thrown. Suppose if I'm talking about the plane, generally we were talking about the ground. But right now I'm talking about the plane that is inclined at alpha. Right. It is thrown with respect to beta. It is thrown with respect to beta at speed u with respect to inclined plane. Say I'm going to give you all the Brahmastra, right, to solve the questions, right, on the projectile on the inclined plane. What is that Brahmastra? Always consider inclined plane as x-axis, perpendicular to it as a y-axis. Things are going to be quite easy for you all. See now what happens. Everything we are going to see with respect to the inclined plane. Everything. Two component of the velocity. U sine of beta. U cos of beta. Trajectory it is going to follow like this way. See, there is only one difference between the oblique projectile and the projectile and the inclined plane. In oblique projectile, horizontal was uniform, vertical was uniformly accelerated. Here, both are uniformly accelerated. Why? One component of G is G sine of alpha, second it is G cos of alpha. To increase and decrease u sine beta, we are having g cos alpha. Acceleration is there in y with respect to the inclined plane. To increase and decrease u cos beta, g sine alpha is there. It means that if I'm talking about the projectile motion, the inclined plane projectile, then something that is contributed into the horizontal, something that is contributed into the vertical. The horizontal contribution is uniformly accelerated and the vertical contribution is also uniformly accelerated. Why? Horizontally acceleration is there, vertically, right, acceleration is there with respect to inclined plane. It means position vector is Rx of I, Ry of j. This is uniformly accelerated. U cos of beta, right, of t minus half g sine of alpha into t square of I. U cos beta is affected by g sine alpha plus u sine of beta of t minus half of g cos of alpha of t square. U sine beta is affected of g cos alpha. This is the position vector. What will be the velocity vector? Vx of I plus Vy of j. U sine u cos of beta, right, minus g sine of alpha of t of j. I'm sorry, I. Plus u sine of beta minus g cos of alpha into t of j. Uniformly accelerated, v is equal to u minus at, u plus at wali equation we did it. Time of flight 2u sine of beta by g cos of alpha. Okay, this much values are important, this much three formulas are important, right? Apart from this, if you are going to get stuck, you're going to get stuck. Okay, so limited questions are going to come from the projectile. In some of the resources it has been told what from top to bottom, from bottom to top, everything is being told. Nothing matters, only one logic matters is this: if you're going to release from top to bottom, right, g will affect like that way. If you are going to release from bottom, or sorry, from top to bottom, things are, this is from bottom to top, from top to bottom, right, the components will get reversed only. That's it. So it doesn't matter to remember the formula, it is matters to remember the way to obtain the formula, right, the way to obtain that specific formula. Apart from this, range is there. Okay, range is there, sorry, range equation is quite simple. Range is equal to u cos of beta of t minus half of g sine of alpha into t square. Can we replace this as time of flight? This is everything with respect to the inclined plane. So r is equal to u cos of beta, time of flight 2u sine of alpha, sorry, minus half of g sine of alpha into 2u sine of beta by g cos of alpha whole square. This is a range. Log equation is going to come and it will get changed from top to bottom and bottom to, but you are all aware of this is the horizontal component of the position and we have to replace time of flight. That's it, rather than to formula, apply the formula and everything. Okay, right, yes or no? So this is how the projectile ends. 30 or more than 30 questions of this projectile, right, okay, will be included in this question, will be included, right. Okay, now it's time to move forward for the some of the another concepts of the motion into the 2D, right, that is the ribbon problem, rainman problem and all of those stuff, right. So let's move on to it. So let's move on to the next topic, the relative motion into the 2D. Right, relative motion into the 2D. See, relative motion into the 2D contains, okay, basically it contains three kind of the problems. The first one is a Rainman problem. The second one is a Riverman problem. Right, Riverman problem is having two cases, right, and we are directly going to deal with the shortcuts. Right, we are directly going to deal with the shortcuts. Okay, so it's relative motion into the 2D. Okay, Rainman problems, Riverman problems, and some of the fundamentals of that. Right, so the thing that we analyzed, relative motion, we have seen into the previous chapter, into the first part. Right, the thing that we analyze into the detail into the previous chapter, the same thing we are going to represent into the vector form. Okay, so I'm going to take the same example of it. I am going to take the same example of it. Now let's understand this stuff. Okay, the best example of the motion into the relative motion into the 2D is Angry Birds. Right, okay. Rather than to move on for it, let's have the very simple example that we have discussed into the previous session. Again, we are going to grab it, okay, and we are going to reach to the deep of the concepts. Okay, so relative motion into the 2D, let's say this is a ground. Okay, okay, this is particle A, this is particle B. But you can say object A, object B. Right now it is a motion into the 2D. We are not dealing with the cause. That's why I am defining it as a particle A, particle B. If we were about to deal with the cause and we were moving on to the dynamics and selecting the configuration of the system, then we might have said, right, that this object right now, okay, whatever the mass it holds, it's only the particle for us. Right, whatever the mass it holds, right, it's a particle for us. Now see, in the previous session we right had an example about the relative motion into the 1D, that A was there having the speed of 15 meter per second and B was having the speed of 10 meter per second. Right, but this time how I'm going to represent, see, three observers I'm going to take. The first, that is observer on ground, right, the second, that is observer on A, the third one, that is observer on B. Suppose A is given the velocity 3I plus 4J. Right. B is given the velocity 5I plus 4J. Okay, A is given the velocity, B is given the velocity. Now it is very difficult to imagine these things, right? To imagine the concept of 2D and 3D, right? Relative motion in 2D and 3D is quite difficult for you all. All the time it is difficult for you all. So in this case, generally what students used to do, rather than to imagine those stuff, okay, immediately they apply the relevant equation and reach up to the solutions. You can imagine Rainman problems, you can imagine the Riverman problems, but it is quite difficult to imagine this stuff because the velocity it is given into the 2D, right? Suppose, see, I can understand, see, let us take an example. Suppose if I am talking about the observer A, with respect to observer A, how B is moving. Practically, if you are standing on the observer A, then it is easy to imagine and you do visualize, yes, this thing is going on. But right now in 2D and 3D, by standing on this position, oh, how B is moving, right? There is a possibility A might be moving like this way, B might be moving like this way. And if we are saying with respect to it, then it's like this way. Okay. So I want to tell you all, rather than to moving on for that approach, let's move on to the very simple thing, right? This is given the velocity 3I plus 4J. This is given the velocity, right? Okay, 5I plus 4J. Suppose if I am taking one as the observer. Okay, suppose, okay, with respect to the observer on the ground, this is the velocity given. Okay, this is the velocity with respect to ground. Okay, that's the velocity with respect to ground. Okay, that's the now. Suppose if I'm taking A as the observer. Suppose if I am taking A as the observer. Okay, now this, if A is an observer, then I must say, right, what will be the velocity of B with respect to A? Obviously, it is going to come up into the vector form. Obviously, it is going to come up into the vector form. Right, so I would define it as VB is equal to velocity of B minus velocity of A. What is the velocity of B? According to the conventions, phi I plus 4 of J, right, minus 3I minus 4 of J. 4J is going to cancel. The relative velocity is going to come upon as 2I. Right. Okay, this will tell what observer on A feels. This will tell. I means what? This I, unit vector I, it is going to create the impact on the observer. Okay, now you can imagine, after evaluation you can imagine what things are going on. Right, this is a small, like, we can say it is a exception kind. I can't say it is an exception, but at this position of the time, students always used to get in a chaos, right? They are always in a myth. Okay, so here now what happens if I'm standing on A? What B is happening with, right? So you can say the vertical components are same. Vertical components of the velocity vectors of the both, right, A and B are same. So obviously they are in the same direction. So they are going to cancel the effect of each other. Right. So the observer on A feels, right, he feels B is moving on positive x-axis with speed 2 meters per second. Right, he feels means with respect to the observer A. He feels, it means that with respect to the observer A, these things are going on. Right, now the same, what happens with the respect to the observer B? Okay, what happens with respect to the observer B? Okay, again, so now what will be the velocity of A with respect to B? It's VA minus VB. Now this time everything is in a 2D, right? See, generally to explain 1D is not a phenomena. Okay, for that reason in physics, first of all, the vectors are covered. Why vectors are covered? Because no one is going to waste the time on explaining the 1D first and then moving on to the 2D, but generally it should be explained individually. Right, that will help you all in grabbing the concept. It should be explained individually. Yes, I can understand it is not following the hierarchy, whatever is the trend, right, that is going on right now into the industry. Both are explained at the same, in the same lecture, right, but it should be explained individually. Okay, now here, what is A with respect to B? This is 3 of I plus 4 of J minus 5 of I, right, minus 4 of J, right. So this 4 is going to get cancelled, right? Velocity of A with respect to B, this is going to negative of 2 of I meter per second. So what happens here? This is a ground, right? This is right of A. Okay, this is B. Now what happens to the observer on B? Okay, he feels that A is moving in negative x direction with 2 meters per second. He is moving, he feels that A is moving into the negative x direction with field. Right? Why? The relative velocity is going to come upon like this value. Right? Observer on A feels that B is moving into the positive x direction. An observer on B feels that A is moving into negative x direction. Why? Because the vertical component of the both of the A, right, will get cancelled the effect of each other. That's why only horizontal relative things are going to get filled. Right. So in this case, I want to tell you all, right, A and B. Now suppose, let's talk about an extraordinary situation in which, okay, suppose this velocity vectors, right, are of the different values. Suppose if the vertical components are not cancelling the effect of each other, right? Suppose, right, the vertical components are not cancelling the effect of each other. Now it is difficult to analyze the situation from the observer point of view. In this situation, what happens with respect to the observer on the ground? A is moving with 3i plus 4j. With respect to the ground, B is moving with 5i plus 4j. But with respect to observer A, B is moving towards positive x direction into the with 2 meter per second velocity. With respect to B, right, A is moving into the negative x direction with the 2 meter per second velocity. That's a difference. The students, the number of the students, those who are able to analyze this example into the most convenient manner, right, they are not going to face any problem into the relative motion like the Raidman and the Riverman problems, right? So it's my advice, if you are facing any kind of the issue or you are having any kind of the doubts, right, so I must say, right, immediately you can revise the video and clear out that stuff. Okay, because if you are not clearing, if the things are not clear, the fundamentals of the relative motion in 2D are not clear at this moment, then things are going to be quite, right, crazy for you all into the next half an hour or 1 hour of the session, right? Next half and 1 hour of the session. Okay, so see, it's a very simple thing. Now suppose if I want to I'm going to give you all a very simple example of that into the relative motion into the 2D. Suppose how to represent the relative motion in 2D. How to represent the relative motion, right, into the 2D. Okay, or you can say how to represent the relative uniformly accelerated motion in 2D. Let's say from the ground's perspective, right? So for that, okay, suppose if you want to represent the uniformly accelerated motion, then I must say this time the acceleration vector should be constant, right? Okay, acceleration vector, I'm not talking about the right value, the acceleration vector should be constant. It means its magnitude and the direction should be constant in 2D and 3D. Then and then we can say the particle is performing the uniformly accelerated motion in 2D. Constant acceleration means what? (2i). This is a constant acceleration. 2i plus 3j, this is a constant acceleration. 3j, this is a constant acceleration, right? 2i plus 4t of j, this is not a constant acceleration. Right? This all are the examples of the constant acceleration. This is not an example of the constant acceleration because here the y component of the acceleration completely depends on the time. The y component of the acceleration completely depends on the times, and yes, things are going to change with respect to time. Okay. So here how we are going to represent the equations of the uniform motion. First, this is the first equation of the motion, right? Position at any time t. Now it's not distance or displacement, it's position at any time t. For that reason, it is always discussed. Yeah, you might have observed into a previous session, it has been always said or mentioned into the question, position versus time graph, position versus time dependency, the position of the particle. Many students might be in the thought, why many times this positions is used instead of distance and displacement. Actually, they are writing things into the generalized form. Whenever any concept is introduced, right, then it is always introduced that it should be accepted universally. But sometimes it happens, right, with assumptions it is accepted universally, or sometimes it happens without assumptions, it is not even accepted universally, right? So this thing always happens. So position at any time t, it's r minus r0. This is the first equation of the motion. Velocity at any time t, v is equal to u plus at. The second equation of motion, the third equation of motion, v square minus u square is equal to 2a dot s, right? These three equations are only applicable, right, okay, when the acceleration is constant. This is an actual concept of relative in 2D. Okay, this is the actual concept of the relative in 2D. Now here comes the two major applications of relative motion into the 2D. Okay, first of all, let's move on to the sum. Okay, this is right, very easy sum. Just hold on. I think these things we have seen. No, this thing we have seen into the police fire bullets. Okay, first of all, let's move on to the rainman and the riverman problem. Then additionally, we are going to see sums based on it, right? Okay, because the riverman and rainman problems are quite important. Okay, riverman and the rainman problems are quite important. Now, what does this rainman problem states? A man in the rain having feelings. Like that way. When we always used to stand into the rain, then right, lots of quotes start scrolling in the mind. Why I walk in rain? Because no one is able to see my tears, right? And suddenly, if in the rain, if you hear this song, right, any respective song, no, this is an actual, this is not a rainman problem into the physics. This is actually a rainman problem into the real life. Okay, this is actually the rainman problem into the real life, right? Generally, what happens when we are into the rain? Okay, generally that happens with all of those teenagers, right? Okay, then they used to Tanhai Tere bin main kaise jiya, like that. And the latest one, tum hi ho, kyunki tum hi ho, like that. Okay. Generally, what we used to think, if it rains, where is pakoda and chai with carom? Okay. So the one who is having this kind of the thought while it rains, that where is carom, pakoda, pyaj wala pakora, bada pakora, pyaj wala with chutney, right, where it is. Then I must say, guys, you all are mature. And if you still think while it's rain. क्योंकि तुम ही हो, अब तुम ही हो. Guys, nothing is going to happen. You are lost somewhere into the mid of this world. I'm there with you anytime. Okay? So from now onwards, whenever it rains, pakora, where is pakora? Chutney wala pakora. Understand? You don't understand? Pakora, chutney wala pakora, barish. Chai, oh, maturity. Not tum hi ho. Wrong way, wrong way. No entry, no entry. Right? Okay, things apart. Let's move on to the actual Rain Man problems. Right? Okay, what the problem man is facing into the day-to-day life. What actual the man is facing into the day-to-day life. Okay, see now. Rain Man pyrobilums. Okay, what does it state? See, entire Rain Man problem, it is based on the single question solving approach. Right? Okay. Single question solving approach. All of the problems, right, the man is facing while moving on to the rain. Right? All problems, whether it is tum hi ho or it is pakora with chutney, all of the problems are having the single solution. What? It's important how rain appears to men. It's important how rain appears to the man. The way, right, the manner, the appropriate manner through which rain appears to the man, this single statement is going to solve all of those Rain Man problems. Right? Whether it is pakora, tum hi ho, or it is a physics. Yes. The single statement it is going to solve all of those problems. How? Very simple. Suppose it's raining. This is velocity of rain with respect to ground into the vector form. Okay. Velocity of rain with respect to ground into the vector form. Here, suppose initially velocity of the man is 0. Initially, right, velocity of the man is 0. If rain appears, let's say if it's raining vertically, obviously it is going to be in vertical, into vertically downward. Obviously it is going to be vertically downward. Now it is going to be vertically downward. Then what happens here? Right? If it is going to be vertically downward, then what happens here? The way it's raining, same it appears to man. The way it rains, same appears to men. The way it rains, same appears to men. But why the way it rains, same appears to man? Because man is stationary. The velocity of the man with respect to ground is 0. As because of this reason, the way it's raining, if it is raining vertically downward, it appears same to the man. Suppose if it is raining at some angle with respect to the vertical, the same way it appears to the man. Suppose it is raining at 60 degree with respect to vertical, let's say 60 degree with respect to vertical. Right? Suppose this is a velocity of rain with respect to ground. The same way it will appear to the man. Why? Because he is stationary. the things are gonna change when, right? Things are gonna change. Suppose it's raining vertically downward, right? So can I say this is velocity of a rain with respect to ground, right? Why we can say this is velocity, right, of a rain, this is with respect to ground? Because here the observer velocity was, the man's velocity was completely zero. But now suppose he starts moving with some specific velocity. Suppose he starts moving with some specific velocity, then what happens here, right? Rain was appearing vertically downward when he was stationary. But when he starts moving, suddenly the rain got tilted at some specific angle. Right? So can I say this is velocity of a rain with respect to man? This is an important thing. How rain appears to moving man. I'm going to give you all the right day-to-day life example also, right? I'm going to give you all the day-to-day life example also that that states that it states, right? The day-to-day life example, right? It states it's a very simple thing, huh? I must say it's a very simple thing. Okay, it's a very simple thing. What it states? It states that suppose we are on our bike, okay, suddenly it starts raining. When the bike velocity or my velocity is zero, rain appears to be fall vertically downward. Suddenly if I'm going to accelerate my bike, it appears in front of me at some specific angle with respect to the vertical. This happens. When we are stationary, rain right, falls vertically downward. Obviously rain is going to fall, okay? But when we are moving into the specific direction, it appears right in front of us at the specific angle. It got from vertically downward, it got tilt, right? It tilts at some specific angle theta with respect to the vertical. The same thing is happening with this man. When he is stationary, the rain is appearing vertically downward, and when he is moving with some specific velocity, that same rain appears to be right at some specific, it gets tilt at specific angle theta with respect to the vertical. Right? So this is it is important how rain appears to moving man. It is important how rain appears to the moving man. That these things are going to define. Slowly, all of those rain man problems, right, we are going to solve. We are going to use the same equation, right, the same concept, and we are going to solve this stuff. Okay. In all of those rain man problems, you have to just think about a single point, and that will be the question solving approach for all of the maximum number of the questions. The thing is how rain appears to moving man. How rain appears to the moving man. Yes or no? Let's have the first problem of it. Suppose velocity of a rain with respect to ground. See, from now onwards, if this terminology it is used, that velocity of a rain with respect to ground. From now onwards, right, you should all be aware of, if this terminology is used, that velocity of the rain with respect to ground is 10 meter per second, then immediately you all should have a click that it is with respect to the stationary man. It is with respect to the stationary man. Velocity of the rain with respect to ground is 10. Right? Okay. Suppose velocity of man is 0. The question states, right, at what degree with respect to vertical man has to hold the umbrella to save himself from rain. And what degree he has to hold the umbrella to save himself from the rain? Right? It's a very simple thing. If man is stationary, how rain appears? Again and again we are focusing on the question solving approach. How rain appears to the moving man? Right? Rain appears vertically downward to the moving man. Rain appears vertically downward to the moving man. So he has to hold the umbrella, right, vertically upwards, right, 0 degree with respect to vertical. Okay, 0 degree with respect to vertical. Slowly when sums are gonna gain, right, change, we are going to improvise it. So we are going to improvise this thing, right? And this sum was quite simple, but now things are going to get changed. See now. Suppose for a stationary man, now see what I told you before, if it is written into the question, the velocity of the rain with respect to ground, that is equal to, right, 10 meter per second, then immediately this terminology should be there into your mind. This terminology should be there into your mind, right? The person who is on the ground, suppose he starts moving with the speed of 5 meter per second. At what angle he needs to hold the umbrella? At what theta? Right? With respect to vertical, he needs to hold the umbrella. At what theta with respect to vertical he needs to hold the umbrella? See what happens here. When he was standing and he was stationary, rain was appearing, right, to fall vertically downward. Now when he starts moving, this is how rain appears to the man. Now at what degree it is appearing, we need to calculate. So first of all, with respect to the observer, what is the velocity of a rain with respect to the observer? Relative, using the concept of relative motion into the 2 dimension, right? Velocity of the rain with respect to ground, it is negative 10 of j. What is the velocity of man with respect to ground into the vector form? Plus phi of I meter per second. Replacing this value, we are getting velocity of the rain with respect to man as negative of phi of I minus negative of 10 of j, right? This is the velocity vector. This is how rain appears to moving man. This is how rain appears to the moving man. Okay, this is how rain appears to the moving man. Now question is, at what degree he needs to hold the umbrella, right? What degree he needs to hold the umbrella? Velocity of rain with respect to man is negative of phi of I, negative of 10 of j. First of all, let's plot this vector on Cartesian coordinate system, right? Let plot this vector on Cartesian coordinate system. Negative of phi of I, negative of 10 of j into the vector. This is the length of the vector, guys. This is how velocity of rain appears to the moving man, right? When man was moving, right, with some velocity, this is how rain appears to the man. Anti-parallel to this, he has to hold the umbrella. Anti-parallel to this, it means if this is a theta with respect to vertical, then this is a theta with respect to vertical. Anyhow, if we are able to calculate this theta, then we are going to get this theta as same, because they both are vertically opposite angles. So how we are going to opt out this from this, the angle from the respected value? From the fundamentals of the vector. If you want to calculate this theta, then tan of theta, that is equal to negative of phi by negative of 10, that is equal to half. At phi is equal to half, at this angle man needs to hold the umbrella with respect to vertical. At this angle, man needs to hold the umbrella with respect to vertical. Yes or no? Man needs to hold the umbrella. So in summarized form, things realized on how rain appears to the moving man. Let's move on to the question and improvise it. Okay, let's improvise it again. Suppose velocity of rain with respect to ground this time, right? Velocity of the rain with respect to ground is this time negative of, or let's say, let's write it technically. Velocity of rain with respect to ground is 10 meter per second at 30 degree with respect to vertical. Velocity of the rain with respect to ground is 30 degree with respect to vertical. It means when man is stationary, when velocity of man with respect to ground is 0, right? I can't say t is equal to 0, but when velocity of a man with respect to ground is 0, rain appears to be falling at 10 meter per second, making degree 30 degree with respect to the vertical. Right? Suppose he starts moving with 5 meter per second. How rain appears, at what degree he needs to hold the umbrella? Simple question. At what theta with respect to vertical he needs to hold the umbrella? Simple. How rain appears to the moving man? This is the velocity of a rain with respect to man, that is equal to velocity of a rain minus velocity of a man. What is the velocity of a rain? See, velocity of the rain is having the two components. This one is negative of 10 sine 30. This one is negative of 10 cos of 30. Right. So this is gonna be, right, negative of phi of I, negative of phi root 3 of j. What is the velocity of negative of phi of I? Right. Because it is moving into, see, for the sign convention I told you all, we are going to follow the generalized approach. Right, this side positive I, this side negative I, upside positive j, downward negative j. The conventions that we are using since long, and the convention that we are going to use till the end of the syllabus. Right. So velocity of the rain with respect to man, that is equal to negative of 10 of I minus phi root 3 of j. Okay, negative of 10 of I minus 5 root 3 of j. This is the vector how rain appears to the moving man. This is the vector how rain appears to the moving man. Now what we are going to see, it's a very simple thing, right? What we are going to analyze, velocity of the rain with respect to the moving man. Okay. Let's plot this vector. Let's plot this vector. Velocity of a rain with respect to man, that is equal to negative of 10 of I minus 5 root 3 of j. Negative of 10 of I. This is negative of 10. This is negative of 5 root 3. Okay. The coordinates, the point at which these two coordinates are going to meet will be the vector. Right. Okay. This is a point where these two coordinates are going to meet and this is a vector. Right. See, this is how the rain appears to the moving man. Anti-parallel to this, man needs to hold the umbrella. Anti-parallel to this, man needs to hold the umbrella. Right? Anti-parallel to this, man needs to hold the umbrella. So it means that we need to calculate this theta, vertically opposite angle, that theta will automatically we are able to reach up to the answer. So tan theta, that is equal to negative of 10 by 5 root 3. Theta is equal to tan inverse of 2 by root 3. At this angle he needs to hold the umbrella. At this angle he needs to hold the umbrella. Right. I'm moving aside on the countdown of 10 seconds. If you want to analyze this stuff, you can. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Let's improvise this. Let's improvise this. I think we have to use red only. Suppose, now see, when man was moving with 5 meters per second, the question states that when man was moving with 5 meters per second, the rain appears to be vertically downwards. See, mark my word, this is not rain with respect to ground. Rain appears to be vertically downwards. Right? It appears to be vertically downwards. Rain with respect to ground was at 30 degree with respect to vertical. Right? So we need to calculate the magnitude of the velocity of a rain. Velocity of a rain with respect to ground, it was at 30 degree with respect to vertical. Okay, the magnitude we are not aware of. But the question states when man was moving, the rain appears to be exactly vertical. So when he was moving, right, when he was stationary, this was the situation. when he is moving, the rain with respect to man is vertical. So we need to calculate the magnitude of the rain with respect to ground. Two-step sum. But first of all, I'm moving aside for the 10 to 12 seconds. Let's give you all, right, 20 seconds, okay, to analyze the situation and solve this stuff. Okay. So it's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10. When he was moving, right, when he was moving with 5 meter per second velocity, rain appears to be fall vertically. It means that, see, the velocity of the rain with respect to ground is having, right, the two component. This is an x component, right, this is a y component. If man is running exactly, see, again I'm repeating that stuff, kindly mark. If man is running exactly with the speed that is matching the horizontal component of the rain with respect to ground, then their horizontal components are going to get cancelled out. Only vertical is remaining, and that appears to moving man. Again, I'm repeating that stuff. When, suppose, or when this man starts moving with the velocity as same as the horizontal component of the rain with respect to ground, if this happens, then both of the horizontal component relatively are going to cancel out, and only vertical component remains, and that appears to the moving man, and that is mentioned into the question. It means that velocity of man with respect to ground is equal to velocity of rain with respect to ground, the horizontal component of the rain with respect to ground. So this is phi. VRG is equal to 10 meter per second. This is a magnitude. It's a two-step question. Sometimes, right, this is a logical question, but sometimes if students are aware of this stuff, right, they can even calculate this orally. They can calculate this orally. Yes or no? They can calculate this orally. Let's improvise this. First of all, we said that man is stationary. Then we moved a man. Then we tilted the rain at some specific angle theta. Then we saw this concept. Now, man is moving with 10 meter per second velocity on the inclined plane. Dhumta na 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 dhumta na na na. Rain with respect to ground, 10 meter per second, negative of J. At what degree he needs to hold the umbrella? Same thing we want to rely on. How? the rain appears to the moving man. So velocity of the rain with respect to moving man, right, that will be is equal to velocity of a rain with respect to ground minus velocity of a man with respect to ground. This time velocity of a rain with respect to ground is negative of 10 of j. What is the velocity of a man with respect to ground? It is having the two component, right? This one is 30 cos 30, right? And this one is 10 sin 30. So it's negative of 10 cos of 30 of I, negative of 10 sin of 30 of j, right? So this is negative of 10 of j, negative of 5 root 3 of I, negative of 5 of j. So velocity of a rain right to the moving man is negative of 15 of j, negative of 5 root 3 of I. I think we need to check it out into the previous question. Did we? This was fine. Negative 10 of I, negative 5 root 3 of j. Negative 5 of I, negative 5 of I. Okay. Okay. Sometimes this happens, right? So this is how the rain appears to the moving man on the inclined plane. Same thing we approached. Let's plot out this vector. Velocity of a rain with respect to man, that is equal to negative of 15 of j minus 5 root 3 of I. Plot out this vector. The point where these coordinates are going to meet will be the velocity of a rain that appears to the man. This will be the angle theta. Anti-parallel to this, he needs to hold the umbrella. So what is the 10 of theta? That is equal to 5 root 3 by 15. 5 3s are. This is 1 by root 3. At 30 degree with respect to the vertical, he needs to hold the umbrella. 30 degree with respect to vertical, he needs to hold the umbrella. Yes or no? 30 degree with respect to the vertical, he needs to hold the umbrella. Right? 30 degree with respect to vertical. So guys, this was all about the rainman problem, and everything depends on how rain appears to the moving man. Okay. Circular motion we are going to cover up. Either circular, the separate video on the circular motion and the motion into the vertical circle will come up. Right. The separate video of the circular motion or the motion into the vertical circle will come up. Right. Or okay, we are going to see that into the work energy and power. Okay, we are going to see that stuff into the work energy and power. Right, everyone? Now, we are going to see the riverman problem. Like the problem man was having in rain, the same kind of the problem, right? The man is having in river. Like the problem man was having in the rain, the same the man is having into the river. The rainman problem was having an approach. Same kind of the approach the riverman problem is having. What you need to follow? the things that happen with respect to the observer on ground is truth. Thing that happens with respect to the observer on the ground is truth. Things that happens with respect to man was the truth. Into the rainman problems, into the riverman problems, things that happens with respect to the observer on the ground is truth, 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 sachai, sachai, sachai. What does this riverman problem states? It is having only two cases. Riverman problem is having the two cases. The first case is minimum time approach. The second is minimum distance approach. Third is the spatial case. Okay, that evolves from the second part only. The first is minimum time approach. Second is minimum distance approach. The third is a spatial case. But what actually it states? Sir, many students might be having the sir. बहुत गुस्सा आ रहा है. Kill you, sir. You told us the approach, you told us but you are not telling us the situation. How you can say, see, you told us first of all that in the rainman problem, rain is there, man is there, but you haven't told anything about the entities that are involved in the riverman problem. Then directly you are discussing the stuff, sir. That this is an approach and this thing you have to do. How? Question mark. The question va ne mark va. Right? See, what is in situation? In all of those cases, same situation is there. Anyhow, man has to cross the river. Suppose this is a river. Width of the river is B. Man is swimmer or man is standing at this point and he needs to reach to the opposite end. Man is standing at the one edge and he has to reach to the opposite edge. B. In all of those cases, this kind of the situation is going to come upon. These all are the applications of relative motion into the 2D. Right? All are the applications of the relative motion into the 2D. In the entire 2D, we are having the projectile axis cases. In summarized form, we are having the three concepts in 2D. Circular motion, right? This one, riverman, rainman, and all of those applications of relative 2D. And its concept, and the third one is projectile. The two things we are about to discuss is we are going to get completed. The third one, right? Some of them teach, like they used to teach this circular motion with the NLM or the work, energy and power. Right? Because the more thing it is going to come upon into the rotation and that part only. Okay. But don't get worried. Either I'll see the planner. Right? If I'm getting an extra time, I'm not saying extra time. If I'm able to do that, I will upload this separate video. Else, we are going to cover up into the work, energy and power. Okay. So this is a thing. Whether the man will cross the river in minimum time or it will cross the river into the minimum distance. River is also flowing. These two cases we need to see, that's it. And the sums based on it. But what will be the actual question solving approach? See, lots of observer we are going to take. One observer we are going to take on the ground. One observer we are going to take on the river. But what will be the question solving approach? The observer who is in ground, things that happened right with respect to the observer who is on the ground, final. Let's see this. Let's discuss this case. The first is the minimum time approach. What actual the situation is and how we are going to discuss that stuff. This is a river, right? The width of the river is B. Man who is on this side of the river at point A, in the minimum time approach, he needs to reach to the opposite side. Man needs to reach opposite side. What happens here? Right. He needs to reach to the opposite side. And this time, river is also flowing with respect to ground. Now what happens here? I told you all we are going to take the two observers. The first observer who is on the ground. The one who is on the ground is going to see the reality. Right. Now in some of the cases, some of the faculties used to take the second observer with respect to river also. No need for that, right? This thing and direct shortcut for the riverman problems, all of those sums we are going to solve it up. Or maximum number of the sums, right? Now what happens here? Man, I'm on this side, swimmer, want to reach the opposite side. Blindly, I am going to jump into the river and I'm going to swim. Perpendicular to the flow of river. Mark my word. Swimmer jumps perpendicular to the flow of river. If river is not flowing, man will start from point A and will reach to the point B if velocity of river with respect to ground is 0. But river is moving with some speed, with some velocity. So what happens? He jumps off perpendicular to the river flow, but river tries to drift him. He is moving perpendicular, river tries to drift him. He is moving perpendicular, river tries to drift him. Then in this case, slowly, right? He reaches to point C. He crosses the river in the minimum time, but destination was not actual. He was in need of. He wants to reach point B, but he did a mistake. He jumped off perpendicular to the river. And what happens here? River tries to drift him. He was moving perpendicularly. River was trying to drift him. He was moving perpendicularly. He was right. So as of that reason, he reached. Task was successfully completed, but with some extra drift. He reached to the river to the opposite side in the minimum time, but the location was not same as he wants to or he was in need of to reach. Suppose I am of the swimmer, right? So with respect to move river, see, with respect to river, mark my words technically. With respect to river, I am moving perpendicular with respect to ground. With respect to river. I'm sorry. Just hold on. Just hold on. with respect to river. I am moving perpendicularly. Is it a reality? No. Why I am not able to see the reality that a river is drifting me? Because I am the swimmer, I am going with respect to the river. Who is able to see the reality? The person who is on the ground. Suppose I am an observer on the ground. Yaar, he jumped off perpendicular to the river. Now he is drifting at some specific path. So he is able to see the truth. This is the path followed. With observer with respect to ground, right? This is the path followed with respect to man, right, in river. This is a path followed with respect to ground. This is a path followed with the velocity, alright, with the man with respect to river. He is moving perpendicularly with respect to river. But actually river is trying to drift him and move him, and he is getting tilted at some specific angle theta. Suppose he is drifted at theta angle with respect to vertical. This is the path followed with respect to man into the river, na? So for this path, the velocity that is coming, it is VMR, velocity of a man with respect to river. This is the path followed by a man with respect to the ground, the observer on the ground. It means the velocity man holds for this path is velocity of a man with respect to ground. Students are able to understand this approach. Things are going to be quite shortcut for you all. Okay? Because I'm going to write off all of those formulas just within 2 to 3 minutes. See. This is velocity of river with respect to ground. This is velocity of man with respect to river. Then this will be the resultant velocity of a man with respect to ground. Can I write it out? Velocity of man with respect to ground square, that is equal to velocity of man with respect to square plus velocity of river with respect to ground square. This is a theta. This comes from the vector addition. This is the width of the river. This is a drift. Now see, shortcuts. First, if suppose this is 90 degree, can I write it at sine of theta? That will be equivalent to VR of G whole divided by Vm of G. Right? Or this is under root of d square plus b square. Can I write it on d under root of d square plus b square? Suppose if I am writing cos of theta, then that is Vm of R whole divided by Vm of G. This is b whole divided by under root of d square plus b square. Tan of theta, that is equal to Vr of G whole divided by Vmr, that is equal to d by b. From all of those formulas you are going to evaluate the sums. Right? From all of those formulas you are going to evaluate the sums. Yes or no? Right? Now what is the time? Time is not relative. Practically time is relative, but we are moving on to the theoretical aspects. From all observers' point of view, time is same. So suppose if you are taking these three values, then time is Vb by Vmr. Suppose if you are taking from this perspective, then this is d by v rg. Suppose you are taking from this perspective, then that is under root of d square plus b square whole divided by vmg. This is the formula for the minimum time. D is a drift, B is the width of the river. So this is the first case, the case of the minimum time. Directly we have discussed. I can't say it is a kind of the shortcut, but things are quite easy. First time he faced the fraud. First time he faced the fraud. A river did a fraud with me. I trusted it and moved perpendicular to it. But he drifted me to the opposite side. I reached on the opposite bank of the river, but with some drift. Yeah, one thing is remaining. What is the total length of the journey? I'm writing here. Under root of d square plus b square. Actually, with respect to ground, this much distance he is moving on. And that is a truth. Right? This is a myth for a swimmer. This is a truth with respect to observer. Right? So this is a length actually he is covering. This all of those technical terms, right, are going to remember. Okay. So wrong thing happened with him. Now this side he wasn't, this time he was in the mood. Right? This is an observer with respect to ground. This time he want to reach from point A to point B. Now he was aware of, river is flowing. So what he did? He jumped off at angle theta with respect to river. He jumped right angle theta with respect to river. River was moving right with respect to ground. First of all, he jumped off perpendicular to the river, so river drifted him at some angle theta. This time he was smite. He jumped off at some specific angle, river was drifting him perpendicularly. He jumped off, he was moving at some specific angle, river was drifting him perpendicularly. He was moving at some specific angle, river was drifting him perpendicularly. He was moving at some specific angle, river was drifting him perpendicularly. So as of this reason, he started from point A, right? And he reached at the point B. So that's why this is the case of the minimum distance. In this case also, thing that is happening, the truth that is happening is seen from the ground's point of view. This will be 90 degree, this will be the theta, right? While moving at some specific angle theta with respect to river, he thought that there is the possibility, I might cover drift, but actual length of the journey is B. I wrote into the third case, special case. In all of those cases, it does not happens that he jumps off at some specific angle theta and he is going to reach exactly at the opposite point perpendicular to the river. No. Sometimes it happens, right? It may jump off right at any random angle. Sometimes it also happens, it may reach to this point C. So this C, reaching this point C is a special case, right? So to solve these sums based on this special case, directly we have to apply the geometry and the vectors, resolving the components. Apart from this, we are having the two cases, minimum time and the minimum distance, right? Things are going to be, right? I'm going to provide you all the shortcuts for it. See now, this is a vector. For a man who swims, he is moving at theta with respect to vertical. So this is velocity of man with respect to river. This is velocity of man with respect to ground. What is the truth? Actually, he is moving perpendicular. What is a myth? For a man who is inside the swimmer, he is at angle theta. What is the truth? River is trying to drift it, or river is drifting it, and he is moving at some specific, moving perpendicular to the river. This is velocity of river with respect to ground, right? This is the velocity of man with respect to ground, right? And this is a velocity of a man with respect to river. Suppose if we are taking this is theta and this is 90 degree, right? Then things are going to be quite easy for us. Right? Okay. This is under root of b square plus d square. This is b. Sine of theta, d under root of b square plus d square, v r of g whole divided by v mr. Cos of theta, right, that will be equivalent to b under root of b square plus d square is equal to v mg whole divided by v mr. Tan of theta, that is equal to d by b, that is equal to v rg by v m of g. Right? Time is same in all cases. If you are writing under root of b square plus d square, vmr. If you are writing d, vrg. If you are writing b, vmg. No one is getting accelerated. That's why we use the equation of the uniform motion. Right? That's why we use the equation of the uniform motion. And in this case, you are having vmr square, right, from the vector form, vmr square, right, that is equal to vrg square plus vmg square. Okay, these are the equations into the case of the minimum distance, right? These are the equations into the case of the minimum distance. Okay, now let's move on to some of the sums of it. The speed of the swimmer into the still water is 20 meters per second, right? The speed of the swimmer into the still water is 20 meters per second. It's okay, it is asked in NEET, right? The speed of the river water is 10 meters per second and is flowing due east. Right? He is standing on the south bank and wishes to cross the river along the shortest path. The angle with which he has to move will be. Second case, the case of the shortest path. It means it is very simple. He is standing at A. He needs to reach B. For this, he had to move at some specific angle theta. Right? So, directly we are going to, this is the velocity of river with respect to ground. How much it is given? It is a flowing, see, this is east. This is he is standing on south. This is east. Right? Speed of the river is 10 meters per second. Right? The speed of the swimmer into the still water. Still water means observer is inside the water with respect to swimmer. Observer, let's take another observer. Right? Observer inside the water or himself, the swimmer himself is an observer. Right? So what here? This is velocity of man with respect to river, it is given. Velocity of a man with respect to river, it is given as 20 meters per second. At what angle he needs to move on? A very simple thing. Right? Directly we are going to take up the formula. Sine of theta, that is equal to VRG whole divided by VMR. VRG is 10, VMR is 20. Sine of theta, that is equivalent to, right, half. Theta is going to 30 degree, right, with respect to vertical, right, 90 plus 30 degree with respect to river flow. This kind of the questions are also coming up into an examination. 120 degree with river flow with respect to the perpendicular vertical is 30 degree. Now, with respect to the river flow, it is 120 degree, right? So here 30 degree with respect to the
stroke with respect to north na, हाँ, तो here this thing will not come up. With respect to north it is given 30 degree will be the perfect answer. Right. See, directly shortcuts we are using up. Question is a PYQ. The width of the river is 1 kilometer. The velocity of the boat is 5 kilometer per hour. Right. Shortest time it is given as 15 minutes. The boat cover the width of the river into the shortest time in 15 minutes. Then velocity of the river stream is what? Right. Velocity of the river stream is what? It is a very simple thing. See. Now this is a case of the minimum time. Velocity of river with respect to ground. Velocity of man with respect to river. Velocity of river with respect to ground. I'm sorry. Velocity of man with respect to ground. Width is given as 1 kilometer. The minimum time, it is 15 minutes. Yeah, can I say that? Velocity of man with respect to river, that is equal to width of the river whole divided by minimum time. Time is minimum for all. If this, see, using this time and width, if we are able to calculate the VMR, then things are going to be quite easy for us. Things are going to be quite easy for us. So what it would be? Vm of R, that is what is width, 1 kilometer, whole divided by minimum time, it's 15 minutes into 60. So VMR, you are going to get it as 4 kilometer per hour. What is the velocity of the boat? VMR, you are going to get the 4 kilometer per hour. Velocity of the boat with respect to ground is 5 kilometer per hour. What is the velocity of the river? Directly Pythagoras. See, this is a shortcut we are going to use. Shortcut we use into the first case. Vmg square plus Vmr square plus Vrg square. Vmg square is equal to Vrg square plus Vmr square. Vmg square is 25 is equal to 16 plus Vrg square. Right, Vrg is equal to 3 kilometer per hour. Simple. A is the perfect answer. PYQ. A person aiming to reach exactly opposite point. Person aims to reach exactly opposite point on the bank of the river stream at this, right? See, now this is a case of the minimum distance. He starts from A and he aims to reach to the exactly opposite point B. Person aiming to reach exactly a pointing point to the bank of the stream is swimming with the speed of, okay, he swims with the speed of 0.5 meter per second, okay, with 120 degree right of the direction of the river flow. Then the speed of the water into the stream will be what? Right. This is 120 degree. This is 30 degree. Right. This is a velocity of river with respect to ground. Directly we are going to use the shortcut. Na? Right. This is what? VMR. Sine of theta, that is VMR whole divided by VRG. VRG, that is VMR whole divided by sine of 30 degree. This is with respect to vertical. So this is gonna be VMR is 0.5 whole divided by half. It is equal to 1 meter per second. The river is flowing with 1 meter per second speed. That's the perfect answer for this specific question. All of those shortcuts we are going to use. So those who are not aware of what shortcuts happen, right, immediately they can move on for this stuff. A boat is sent across the river with the velocity of the 8 km per hour. If the resultant velocity is 10. Yaar, very simple. Boat is sent. Okay, resultant is 10. 10 square is 8 square. Right, plus VRG square. right? Very simple. VRG, it is equal to 6 km/h. B is the perfect answer. Thank you. Okay guys, so as I told you all, this was all about the motion into the 2D. And yeah, again I'm reminding you, if you all like the teaser, I will be waiting for all. This time the teaser was awesome, right? Okay, I did a lot of work behind it. So if you really liked it guys, then I will be waiting for all of your comments beneath the video regarding my content and also regarding my teaser, because that is for you all. The entire PW team is for you all. Right, we are doing a lots of initiatives for you all. Lots of things are going on. As you all know, the PW is a box of surprises, right? And especially PW English. Okay, all time the improvisations are going on, especially into the physics lectures to give you all that stuff, right? Okay, guys, so it's time to go. This is Indrajit Singh. Right, again we'll come back with a new NLM, and as usual, I told that circular motion will be covered into the. Right, either we'll have a separate video on the circular motion and the motion in vertical circle, or we will cover up into the work, energy and power. Okay, so guys, it's time to go. This is Indrajit Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side, bacha. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. Bye bacha ji.